In this video, we are demonstrating power exploration using EnergyLab LITE for the NXP i.MX 8ULP processor. First, developers start with power measurements on the i.MX 8ULP EVK, running a use case based on the NXP power application node. Second, developers verify the accuracy of the simulated power in EnergyLab LITE against the measured power running the same use case. Third, starting with the NXP use case, developers modify the simulator to reflect the specific hardware and software of their own application. Lastly, using the EnergyLab LITE simulator, developers explore alternative hardware and software configurations in simulation to improve power consumption without investing time and resources to develop a custom board, system drivers, and application software for the purpose of measuring power. I'm starting EnergyLab on my PC, and I will connect to the EVK board using EnergyLab's test and measure feature. I do have the EVK board here on my desk, and I'm connected via USB debug cable. Here we see the measured data on the 8ULP EVK in table form on the right and graphed in the main area. I also have terminals attached to the two UART ports on the EVK, one of them connected to Linux, the other to the seed firmware running on the Cortex-M33 processor. We can see that the idle power consumption is around 370 milliwatts at the moment. Now I will enable the display, which increases the power consumption to around 390 milliwatts. Next, I am launching the application, which periodically alternates between processing data and idling, and we can see the power consumption of around 460 milliwatts when active and around 390 milliwatts when idle. We will now start the EnergyLab LITE simulator. The simulator will let us see the detailed power consumption of the EVK for the use case we would like to investigate. The stimulus for our use case is captured in a scenario. A scenario consists of a sequence of timestamps and events, shown here on the left. We are starting off with a scenario that replicates the use case we have just seen on the physical hardware. I'm now stepping through the scenario, and as you can see, the simulation shows around 370 milliwatts when Linux is idle and around 390 milliwatts when the display is enabled, which is in line with what we measured earlier on the EVK. Once we run the scenario to the end, we see 5 iterations of the use case where we are alternating between processing data and Linux being idle. When we look at the component state details here, we can see that the Cortex-A35 application processor is staying in the active state. Further details about the power consumption and power states of all the components are shown in the table at the bottom. Now we would like to know what the energy profile for our use case would look like if we moved the display handling to the Cortex-M33 instead of using the A35 processor running Linux. For this purpose, we will edit our scenario, replacing the display driver software with the equivalent M33 software. The software is described using the EnergyLab task construct. Tasks represent the influence of the software execution on the energy behavior. The key difference in the LVDS M33 task is that the software is running on the M33 and does not depend on the A35. Otherwise, it still depends on the LVDS controller and the 2D GPU to generate the pixels. Now, if we look at the graph, we can see that in the original scenario, the M33 was in a sleep state throughout the original use case. So now that we have moved this task to the microcontroller, we can expect the M33 to be active and thus consuming some additional power. Before we run the new scenario, we will save the current energy profile as a baseline to help us visualize the changes in power consumption. Now we restart the simulation with our changes, and as we step to the moment where we launch the LVDS M33 task, we can see that the power consumption is now actually 26 milliwatts higher than it was earlier. This is what we expected because we are now also keeping the M33 in the active state. But now, as we continue our use case, we quickly see the savings potential shown here in the shaded area, every time Linux is idle, because now the A35 is able to enter a low power state. Down in the status bar, we can see the overall energy savings for our use case, which comes out to around 18% of savings. This should not only reduce power consumption, but should also help to lower the temperature of the device or allow for increased performance at the same power and temperature levels. In conclusion, in this video you've seen how EnergyLab simulation provides an efficient way to quickly evaluate power management trade-offs, saving time and effort when optimizing power for your design and application. Thank you for watching.